Welcome to this introductory unit in the context of advanced topics in the field of the DEM. Let us briefly check of what you will learn in this unit. First, we will talk about the success of the DEM. Then we will recapitulate a key concept, namely the contact force calculation in the soft sphere DEM-based simulation. Furthermore, we will discuss the essential inputs to a DEM simulation for various flow situations together with typical results. Finally, we will also listen to experts on their opinion on why DEM advanced topics should be taught to a broader audience. Before we can start, let me summarize in a nutshell of what the DEM is. Unlike a so-called continuum or Eulerian model, the DEM is a discrete or Lagrangian model. The DEM focuses on individual particles and how interactions between particles and walls or an ambient fluid govern their motion. On the top left, you see a brief summary of Eulerian methods. The key feature is that discrete entities like particles or atoms are smeared out over a representative volume element or RVE. Balance equations can then be formulated for these RVEs. The method is often used in the context of classical CFD simulations. We will also use this word later on. Predicted quantities are the velocity u and the pressure p in each of these RVEs. On the bottom right, you see the other group of methods, the Lagrangian methods, in which we track particles in space and time. These particles, or sometimes parcels as in some applications, as we will see later, are the basis for our balance equations. As you know, the DEM is part of this group of methods. The primary predicted quantities are the particle position x and the velocity v. Well, I think we are now ready to start with success stories connected to the DEM. Thus, we are asking the question, why is the DEM so successful? The key to the answer to this question lies in the numerous applications of the method. A very important and obvious set of applications are mixing and discharge simulations. For example, we can consider the velocity distribution and the dispersion pattern in complex shaped machines, such as a twin screw extruder or mixer. This is very important for optimization studies, for example. On the right, you see a DEM simulation of flowing cylinder-shaped particles. They are just about to exit a hopper. This is of fundamental interest as well as relevant for packaging applications, for example. In these applications, the size distribution of particles can be important. More on this later, as well as a proper set of parameters. Hence, calibration is typically used, as you should have already learned in our previous course. Another very interesting group of applications is the field of agriculture. For example, using non-spherical particle models, one can model the collection and processing of hay, for example. As you see here, complex moving parts can be part of such a simulation. If you watch closely, you can even see that these needle-shaped particles can break, forming short hay fragments. Again, these are important simulations used in virtual prototyping. But the DEM is even more versatile, as you can see here. We can use the method to even study the breakage or comminution of particles. Clearly, DEM can be helpful in particle production processes, e.g. to optimize these processes or troubleshoot an existing process. We can now climb to the next level and couple the DEM to CFT. In this specific case, we also consider the concentration of a reactant in the pores of the particles. As you can see, depending on the speed of the reaction, the concentration is highly non-uniform, as you see on the left, or relatively homogeneous, as you see on the right. Data from such simulations is useful to explore potentials for optimization or to judge the feasibility of a scale-up of this process. The example I will close with is battery research. Here particles play a central role in the manufacturing of cells, their recycling, and in safety considerations. On the right, you see particles ejected from battery cells through safety openings. Of course, such a situation may only happen in case a cell is damaged or severely overheated. In such applications, we see very high temperatures, 1000 Kelvin or even higher, and extremely rapid dynamics. Micro to millisecond timescales need to be considered in such simulations. Since precise measurements under such conditions are challenging, CFD simulations in battery and or high temperature applications are very helpful. They can save a lot of time and money. Please note that particles in such a simulation can also be grouped to parcels to reduce computational entities to be tracked. Also, we have to limit the width of the size distribution in such simulations to make these simulations feasible. Let us finally sum up why DEM modeling was so successful. This is illustrated by the following 3 AI-generated images. First, industrial processes and the associated engineering disciplines can greatly benefit from the DEM simulation method, mainly due to improved process understanding and optimal processes. Second, geophysical applications such as sediment transport and other applications in the earth and planetary sciences have contributed to the success of the DEM. Third, there are agricultural and biotechnological applications in which DEM showed its strength. The hay harvesting machine was just one example out of many.